please. Okay, class, today we're going to start with a new topic. We're going to talk about magnetic field. Okay, so can you see the PowerPoint? Anyone?
Yes.
Can, okay, good. Okay, students, so how many topics are there in A2? We have 16, 16. So out of these 16 topics, 2 topics is one long-winded, very long, might take 2 weeks. So one of the 2 topics which is long-winded, one of them is magnetic field. Okay, the one we're going to do now. Okay, it might take about 2 weeks. It's a very long topic. Okay, and another one topic which is going to be very long-winded again, might take 2 weeks, is later quantum physics. That's later. Topic, if I'm not mistaken, topic 12. Topic 12, quantum physics. Okay, so magnetic field. So this is the last field we're going to cover up in your physics discussion. So far we'll discuss about electric field. We discuss about gravitational field. Okay, so electric field, a region where charged particle experience force. Gravitational field, a region where mass object experience force. Okay, and yeah, anyone? What is magnetic field? Anybody? What is magnetic field? A region
where a magnetic force is experienced by a magnet, a current carrying conductor, or a moving charge.
Very good, very good. Perfect, good. So a lot of you make a revision. The magnetic field is a region where a moving charge particle, or a magnetic materials experience force. Good. Okay. What is the use of gravitational field? What is the use of gravitational field? What I told you. Use of gravitational field is satellite. Okay, for us. What is the use of electric field? Maybe photocopy machine. Anything else about electric field? Yeah, mainly photocopy, and in scientific research, nuclear field, we use electric field to accelerate them. Yes. Okay, out of these 3 fields, the most useful for humankind, I think magnetic field. Okay, magnetic field, a lot of use. Can anyone tell me what is the use of magnetic field for us?
Generate current.
Yeah, generate current. Very good. No magnetic field means no generator, no motor, no MRI. Even in magnetic field, in a medical field, we use magnet to getting images. MRI, best what you call scanning technique. What else? Your hard disk. Now your hard disk last time was magnet. Now it changed to SSD. So phased out from magnetic field already lah. The disk type of hard disk is using magnetic field. Now we use SSD, and yeah, your bullet train, the one used by the Japanese, the bullet train, and also in China now. The magnetic levitate train. It's a magnetic levitate train. The train was floated on a magnetic field and moved forward. So therefore, frictionless surface. So it can move very fast. What is the speed of bullet train? Anyone? Anyone experienced going to Japan and ever had a ride with the bullet train? What is the maximum speed they can go? Around 300, I think. 360 kilometer per hour. Anyone can check from the net. What is the speed of a bullet train? You use your phone, I think. Can check for me. What is the maximum speed of bullet train? Yes, anyone? 360?
320 kilometers per hour.
320 kilometers per hour. So 300 plus. Okay, so from Cal to Ipoh, with you, we have a bullet train. I think you can reach within maybe 40 minutes. So it's quite fast. So it uses magnetic field. Okay, so history about magnetism. It found in Greek 2000 BC before. Okay, found an abundance of magnesia in northern Greece. It is believed that the word magnet is originated from there, from Greece. Okay. So Chinese use the magnet. Recorded that as early as 2000 BC, the Chinese use as a magnetic needle, always point to the north-south, and have been using to show direction. So they are aware of existence of magnet, but they don't do any further research. Okay, so magnets are material that attract certain types of material, only certain types of material, iron, okay, iron, steel. There is an axis of force. Substance sensitive to magnetism is iron, nickel, and cobalt. Copper, aluminium are non-magnetic. So why magnetic materials have their magnetic moments? Electron spins align. Yes, it seems every atom in the magnetic material has a magnetic moment. We call it. Okay, when there is no external magnetic field applied, it seems that each atom magnetic field it seems random. They are random. Okay, when you apply an external magnetic field, like how do you can magnetize? How do you make a permanent magnet? Anyone? I think this is your O level or SPM knowledge, right? How do you make a bar a steel bar maybe to become a permanent magnet? What do? You put the magnet inside
Coil wire.
the coil. Use what type of current? AC or DC? AC or DC? Use DC. Use DC power supply. So that the coil going to create a magnetic field. The magnetic field going to interact with the atoms inside this bar. So the atom which is not aligned at the beginning, when you give external magnetic field, all start to react to the external field. So all atoms going to start to align. So they all the magnetic field uniform create its own magnetic field strength. Those magnetic field strength. So magnetic materials has magnetism, but the atoms are not aligned at the beginning. Okay. So if this magnet, if after you do magnetized, you become permanent magnet. How do you lose this magnetism? When you drop permanent magnet quite frequently, the magnetic field going to be random again, so it loses magnetism. Okay, two ways to make permanent magnet lose magnetism. One, dropping frequently. Another one way is anybody? Another one way how to make the permanent magnet lose its magnetism. Use the same coil, but use what?
Reverse.
Don't use DC, use
AC.
AC. Use AC. AC current flows opposite direction every time. So the atom going to change direction frequently until it become random, like loses magnetism. Okay. So you have a magnet, you crack into three, they create the south pole, north pole at the edge again. So magnet always dipole. Okay. Electric field, we found monopole. Electric field, positive charge can exist alone, but magnet we don't see monopole. Only north alone exists. We never seen that. It always dipole, not always together with south pole. Okay. So now your question for this question: a free moving magnet will always align itself to the north-south direction. Why? So why always a needle always pointing to the north-south direction?
The Earth
Because
has magnetic field.
Earth has its own magnetic field. So the Earth has its own magnetic field. So the compass the magnet going to align to the Earth magnetic field direction. A bar magnet hung freely in the north-south direction. This is because the Earth is a giant magnet. So Earth itself has a magnetic field. The Earth magnetic field is weak or strong or weak?
I mean, technically, um,
What do
in
you
the
think?
Earth size scale, it is strong technically.
So the size of the Earth is so huge, but the field, magnetic field is very weak,
Oh, okay.
not strong. It's very weak. Where you can find the strongest magnetic field? On the surface of the Earth. Man-made machine. Anybody?
Oh,
Where we can find? In hospitals or MRI.
my.
Okay, MRI uses one of the strongest magnetic field. Uh, okay, we will discuss that. What is the unit for magnetic field? Anybody? It's Tesla. Okay, Tesla is the unit for magnetic field strength. Okay, the most strongest field strength is MRI 3 Tesla. Okay, 3 Tesla. So we will discuss about that. Okay, now the definition of magnetic field. Magnetic field is a region of space where a charge moving obliquely or moving charge experience magnetic force. Okay, what is electric field? A region of space where charge particle experience force. That's it. Whether it's moving or not moving, electric field going to exert a force. But magnetic field is a little gentleman. The charge moves, cuts the magnetic field line, then only a force will be exerted on the particle. As long as the charge doesn't cut the magnetic field line, you won't get magnetic field strength. You won't get magnetic force. It's a little gentleman magnetic field. Okay, so these are the two experiments like your old TV, actually old TV using an electron go and hit the screen. So when you put a magnet, the image will be distorted because the electron which is coming out from the screen, coming out from the tube, it's a cathode tube actually, it will be deflected to one side. Okay, so our main what you call important here is you need to know how to draw the magnetic field strength. Okay, so I go straight to the pattern. These are the okay. How do you find the magnetic field strength pattern? By using a iron filings, right? Iron filings. Magnetic field lines can be traced by using iron filings to show the line pattern and a compass to show the direction. Okay, you place a small thin cardboard on top of the magnet, then you pour some iron fillings, you tap at the side, you can trace the pattern, but it won't show you direction. To get the direction, you must use a compass. Okay, use a compass, it will tell you which direction is the electric field line. Okay, so this is the field line, you know, since from 3, I think, from 4, your early studies, this is the pattern you have to remember. Okay, so here the separation between the lines tells how strong is the field. Further apart, more weaker. Closer, more stronger. Same idea for gravity and electric field. Okay, there are two ways of creating permanent magnet. There are two ways to create a magnetic field by using a permanent magnet or current carrying conductor. Current carrying conductor, coil. Coil can give you a magnetic field. Permanent magnet can give us a magnetic field, which is very useful for human. Which is more versatile, permanent magnet or current carrying conductor? Which is more versatile for human? Current carrying conductor, magnetic field due to current carrying conductor or permanent magnet? By using a coil or by using a permanent magnet preferred by human? By using a current carrying conductor. Why? Because the strength you can vary. You can vary the strength. It's very versatile. How do you increase the magnetic field? Then give more current. More current, you get more stronger the magnetic field. But permanent magnet, the field strength is constant. Okay. So current carrying conductor, magnetic field due to current carrying conductor, more versatile. Okay, I straight go to the pattern. These all are patterns. Okay, before that, 3 patterns you have to remember. 3 patterns you have to remember. First pattern you have to remember is, okay, I go to the next page first. The first pattern you have to remember this pattern. The magnetic field strength due to a current. Okay, when you have a wire, current goes up, you find the magnetic field, and there is a magnetic field surrounding it. Okay, and the current flows up, use a right hand grip rule. Use a right hand grip rule. Your thumb points the direction of the current, your finger tells the direction of the magnetic field strength direction. So when you view from the top, so clockwise, anti-clockwise direction. So these are the field pattern looks like. It's a circle. Okay. Okay. This picture, the one I'm showing you, see arrow. This picture, this diagram, there is one mistake. Anyone can find out the mistake. If 2 marks given for this pattern, only 1 mark will be given. 1 mark is lost. Why? What's the mistake? Same mistake done here too. Both are one mistake. What is the mistake? Anybody?
The field line is consistent.
Yeah, the field line separation. How it should be?
Further away when when the distance increase.
Yes, very good. When go away, make sure the distance is increased. If this is 1 centimeter, this is 2 centimeter, 3 centimeter. Clearly show that in exam. It's 1 mark. Okay, good. So right hand grip rule. You learned this before, right? Okay, so that's the first field you need to know. Second field you have to know is magnetic field caused by a coil. This is a coil, current goes up, current comes down. So use a right hand grip again. Here the right hand grip on your left side, show your thumb upwards. So your finger going to be anti-clockwise again. And here the current going down, use the thumb point down on your right side. Current flows in a clockwise direction. But at center, the both field are moving the same direction, so the field gets strengthened, stronger. So this is the pattern you have to remember. Okay. Okay, out of these two, the most important, of course, the field produced by a solenoid. Okay, this is the most important one. The solenoid, if you have a solenoid, a coil of wire, okay, you have to know which direction is north, which direction is south, and so on. Okay, you see the direction, the picture above here, top here. So the cross means, remember, cross means current flow into the page, out of the page. Cross means the current flow into the page. Okay, it's into the page. Dot means the current flow out of the page. Remember, expected to remember. You can now see here the current is coming out from the top, going down. So use a right hand grip rule again. Use a right hand grip rule. Current coming out from the bottom, sorry. Current coming out from the bottom, current going in at the top. So use a right hand grip rule. Your finger now. This is something to remember. We use still right hand grip rule, but now the finger is going to be your current. Okay, your thumb going to be what? Thumb pointing your north pole. Okay, for the early diagram, for this one, the thumb is your current, your finger is your magnetic field. This to find magnetic field pattern for current carrying conductor. When come to solenoid, want to know direction of the magnetic field, we use the right hand grip rule, but finger is your current. So here you must put a finger like which direction? Here your finger must lift this, go up. So your finger must be upwards. Your finger should be like this, right? I think your point should be pointing this way. So this is your north. Okay. Okay, so finally, you have to know this pattern. You have to know the coil pattern. You must know the solenoid pattern. Okay. So the other two is not necessary. This permanent magnet, this, sorry, this also, the straight conductor. Okay. So now the question is our focus to solenoid. 3 ways. How you can strengthen the magnetic field produced by a solenoid? Anyone? How do you strengthen the magnetic field produced by a solenoid? First is what? Increase the
Increase the
more voltage or more current. Next, anybody?
Number of coil.
Number of turns. Very good. Number of turns. Number of turns or number of coil. Number of turns per unit length. Okay. Third is your placing a soft iron inside the what do you call inside the coil. Place a soft iron. Wind the coil on a soft iron. So the both field will be work together to get a very strong magnetic field. Place a soft iron inside the solenoid. Okay. Yes, so that's the beginning part, introduction. Okay. You check my notes, there are 3 PowerPoint actually for magnetic field. And this is the first PowerPoint discussing about magnetic field. Okay. Okay, so we go to the next one immediately. So now it's 9.2. So magnetic field, electromagnetism. We're going to talk about electromagnetism. So first part, we're going to talk about force acting on a current carrying conductor. Okay. So see this diagram. What is magnetic field? We already explained to you what is meant by that. When a current carrying conductor, this your rod is a current carrying conductor. When there is a current flow and you put a external magnetic field on it, what happened? The bar magnet will experience a force. Okay, you learned this before, right? Okay, what Fleming rule do you use to find the direction of the force? Fleming left-hand rule or right-hand rule? Use Fleming left-hand rule, right? Use Fleming left-hand rule to find the direction. Okay, I'll come back to that rule again. But last time we learned Fleming left-hand rule to find the direction. But now, how big is the force? That's what you're going to learn in A levels. A levels, they introduce a formula. This is the formula to find the force. The force for a current carrying conductor is found to be BIL sine theta. Okay. So here, F is the force. P is called magnetic field strength. I is the current flow in the conductor. L is the length of the conductor in the magnetic field strength. Length, be careful, length is only the length inside the magnetic field. Let's say the magnetic field region is, I'm drawing on top, the magnetic field region is about 10 centimeter only, and you put a rod which is 40 centimeter, but the magnetic field is only 10 centimeter of region. So the L you must use is how much? You must use 10 centimeter. Okay. So the L here is the L of the conductor within the magnetic field. And finally theta. Theta, you see this second diagram here. The theta is angle between the magnetic field direction and the current direction. That's your theta. Okay. Remember, sometimes when because you want to make the conductor become vertical, you must make the conductor become vertical. So you open the angle, so it should be sine theta. So F equals to BIL sine theta. Okay. So you see the first diagram. How do you make the force get larger? Very big force. So you increase the strong magnet, more current, greater length in terms of make the magnetic field more wider, and the theta you make it how much is good. Theta, you get the maximum force, make the theta is 90 or 100, 90 or 0. Make it 90 degrees. That means when the conductor is perpendicular to the magnetic field, the force exerted is the maximum. Okay. Okay, so still your old idea, but now a formula is introduced, how to find the force. Okay. So the direction of the magnetic field, this is your whole idea, right? Use Fleming left-hand rule. Your thumb is your force. Your index finger is your B, magnetic field strength. Symbol for magnetic field strength is B. And your middle finger is your current. Okay, FBI. Okay, or some use as a mother, father, children also can. So your thumb is magnet, your index finger is force. I don't know, mother, father, children. Sorry, father, mother, children. Made a mistake. So father first, force up. Your index finger is magnet, and your middle finger is current. So up to you lah. Whatever idea you remember short easily. Okay. Okay. This picture is about magnetic field induction. This is not electromagnet. I need to remove this. This electromagnetic induction. So this diagram, you can't use Fleming left-hand rule. Okay. So this induction, I will discuss that later. Okay, now, the definition for magnetic flux density. What is magnetic flux density? Magnetic flux density, magnetic field strength, same. Okay, let's recall. What is gravitational field strength? Force per unit S. What is electric field strength? Force per unit, positive charge. What is magnetic field strength? What is magnetic? Magnetic field strength is a little complicated definition. How to get magnetic field strength? F equals to BIL just now, sine theta. Okay, but we use BIL, sine, you take it as 90. So we make the B as a subject, F over IL, we define from here. So what is magnetic field strength? It's the force experienced by a unit length conductor placed perpendicular to the magnetic field. You must say the word perpendicular because sine theta we never write here because we take sine 90. And only sine will missing, right? Sine 90. So we have to say perpendicular, place perpendicular to the magnetic field and it carries a current of 1 ampere. Okay, best you put all quantities. Easiest way, what is magnetic field strength? Is the force per unit length per unit current flow placed perpendicular to the magnetic field. That's your magnetic field strength. So 4 things you have to tell. What is magnetic field strength? Magnetic field strength is defined as the amount of force experienced by a conductor per unit length per unit current flow placed perpendicular to the field. Okay, remember 4 things. Gravity, electric field strength, easy. Force per unit mass, force per unit positive charge. Magnetic field strength, force per unit length per unit current placed perpendicular to. Okay. So the unit for magnetic field strength or magnetic flux density is called Tesla. Tesla, electric car. Yeah, what do you know about Tesla? Tesla is the Elon Musk, right? The who build make the electric car quite a what do you call it? Commercialize the car. Okay, but what is Tesla actually? Tesla is a scientist, right? Okay, Tesla is a scientist who are very quite genius. Yes, very good. Is genius. But problem is not a good businessman. It's not a good businessman. Okay. Yeah, but his idea is very good. The idea he contributed is about alternating current and about the Tesla coil. Tesla coil, something to do with coil involving magnet. So to appreciate his contribution, they give magnetic field strength his name, Tesla. Okay. So 1 Tesla means it's actually Newton per meter per ampere. Force is Newton, current is per ampere, length is per meter. So Newton per meter per ampere, given name Tesla. Okay. The unit Tesla, 1 Tesla is a big unit, like Farad, your capacitor. 1 Farad is a very big capacitance. So Tesla also the same thing. 1 Tesla is a very big unit. Okay. So yeah, electromagnet capable of giving 1 Tesla. The Earth magnetic field is just about 50 micro Tesla. The Earth magnetic field is only 50 micro Tesla. It's very weak. Okay. As I said, MRI is 3 Tesla. But the maximum Tesla ever produced in a scientific lab, okay, is about 1,200 Tesla. Okay, 1,200 Tesla, the maximum we ever created. But the one we practically use is in MRI, 3 Tesla. Okay.
Teacher.
Yeah.
In the diagram, right? Should we use the left hand rule or right hand rule?
Oh yeah. Again, this picture is wrong because this picture is it's electromagnet induction. I wrongly placed this picture because you have a motor, you have generator, right? Moto is what? Moto what plus what you get finally? Moto you apply what? You apply current. Inside the motor you got magnetic field, so you create force. Okay, that's moto. Okay, we are discussing about moto now indirectly. So use Fleming left hand rule. Fleming left hand rule. Generator, what you give to the generator? 2 things, and what you get in generator? Anybody? Generator, what do you apply? You apply force. You push, you turn the generator by maybe the water or wind, anything. Turn the turbine, turn the generator. So we apply force. Inside generator, there is a magnetic field strength, so you get current. This called induction. Induction. This we use Fleming right hand rule. Right hand rule. Currently, we are not discussing the generator yet. Okay, we are not talking about generator yet. We are talking about motor. So it should be Fleming left hand rule. So in the net, right, you will have 2 pictures. You will have a generator picture and motor picture. This one is generator, so you can't use this. This picture diagram is wrong. How do you know it's a generator or motor? If it has a battery, then it's a motor, the one we are doing now. So this diagram cannot be used. Okay. Okay, Shike, can you understand? So
yes.
okay, guys. So a new formula: F equals to BIL sine theta. Okay. So you see this one example. A wire carrying 10 ampere, 2 meter in length, is placed in a field, flux density 0.15 Tesla. What is the force on wire if it is placed right angle to the field? 45 to the field, along to the field. Without calculating, tell me A, B, C, which is going to give the greatest value? Of course, A, right? Put a right angle, then the force is the highest. So A, BIL sine theta, theta is sine 90. You put the conductor like this, magnetic field here, 90, yield the greatest force at 3 Newton. You put the conductor, the current flow, and the magnetic field parallel, you get 0 force. Okay. Yeah. So I think this is easy. Any questions from here? No questions. Okay. Read the question, look at the solution. Just okay. This question is a little unique. Unique in terms of what? In terms of length. The total length of the conductor is 90 centimeter, but the magnetic field is only 20 centimeter long. So L you must use is 20 centimeter. Okay, important. Because it's always already perpendicular. They never said about angle, so we assume it's perpendicular. Okay, so if they never give angle, we assume it's perpendicular. So sine theta, we just make it as 6 Newton. Okay, now look at this diagram. Okay, time to retest your Fleming left-hand rule again. Use your left-hand rule. Fleming left-hand rule. The cross tells the magnetic field is into the page. So point your index finger into the magnetic field, your index finger into the page. Then your current is downwards, current is flowing down, FBI, current down. Use your Fleming left-hand rule. So the force must be to the right. Okay, force must be to the right. You know Fleming left-hand rule since 2 years, right? So I hope recall back. Okay. This is also another unique question. Okay, read the question, look at the solution. Any part you don't understand, just give you 1 minute. Okay, so you read the question. I believe you read the solution. Any part you don't understand. So they have, this is a plain view, the view from the top. The magnetic field is radial, going inwards. The center is north, the side is south. So the magnetic field is outward, going outward. Radial field, radial means is like it started origin from a center point. There is a ring. Ring carries a current placed inside this magnetic field. The between this is a empty slot. So current is flowing clockwise. So which direction is the force? Sorry, they're asking what is the force? The wire has 100 turns. This is something new. 100 turns. If you got 100 turns, the length will be, of course, the length is 2 pi r, the circumference of one circle. But because you got 100 turns, the total length is 100 times 2 pi r. And this is your total L. Okay, so BIL sine theta. Sine theta again is 90 degrees. You see the conductor at every point. If I choose the east side line, see the east side here. The conductor carries a current down. The magnetic field is to the right. So they are 90 degrees. They are 90 degrees. So sine 90. So sine 90 is 1. So we ignore the sine theta. So you get the force 62.8 Newton. Okay. So using Fleming left-hand rule, the force directed out of the page. Do you agree to that? That force on the ring should be out of the page. How do you know? Maybe you can choose one point. Maybe I can choose the left point here. I choose the left point here. The point here. So use your Fleming left-hand rule. Magnetic field is to the left. Okay. Current is where? Current is going upward at that point. So use your Fleming left-hand rule. Current upward. FBI. The middle finger is upward. Magnetic field is to the left. So where's your thumb pointing? Your force. Force should be out of the page. Okay, class. Okay, direct out of the page. So directed out of the page. Okay. I think the most problem here is students sometimes mistakenly use right-hand Fleming rule. Okay, right-hand Fleming rule. Those who are left-handed, you feel convenient to use the right-hand rule. Okay, so be careful. Those who are left-handed, don't use right-hand rule. Just drop your pen, use your left-hand rule. Left-hand Fleming rule to find the direction. Don't use your right-hand rule. Okay. Anyone left-hand here? Left-handed? No one is left-handed. Okay, those left-handed, be careful. Okay. Okay, this is another one question. Magnetic levitate train, the idea. Okay. Read the question, look at the solution. Okay, so I hope you understand. This is the method the magnetic levitate train works. When the train compartment is placed on the track, okay, a magnetic field is applied at the rail. What happened? There is a force, magnetic force will be exerted on the train upwards. And for the train to float, the magnetic force to be exerted upwards must be equal to the, at least equal to the weight of the train. Then the train start to float. So what force need to be applied? What is the magnetic field strength required? So the magnetic force must be equal to the weight of the conductor. In this case, the train is like referring to the conductor. So BIL sine theta must be equal to the mg of the conductor. So from here we can find what is the current required, 5.89 ampere. Okay, 5.89 ampere. Okay, but for the train, the current going to be huge. Okay, but huge current is supplied to the train. And normally they use superconductor for the train. They use superconductor. Okay, they use superconductor to produce the magnetic field strength, because superconductor a reasonable voltage enough to produce a very high current. Okay, because V equals to IR. Superconductor has a zero resistance practically, so a small voltage can give a infinite current, a big current. Okay. Okay, so I skip this first. I go to the Word file. Oh, sorry, not this one. Okay. So this is your notes. So we learn about concept of magnetic field. We done about current carrying conductor. We done the first two. So what is magnetic field? Just now we discussed the region of space or moving charge particle experience force. Uniform field, non-uniform field. Can you draw how the uniform field pattern looks like? Uniform field, draw the line parallel. Equidistance, parallel. Non-uniform field, maybe you can draw 3 lines getting closer. Okay, this is your non-uniform field. Draw the 3 patterns. Long wire carrying conductor. I think long wire, this is the pattern. Circular coil, you have to know how to draw the pattern. And finally solenoid. Okay, solenoid, how the pattern should look like. Which is north, which is south, need to identify. Okay, solenoid, I think I never really tell you about the solenoid. Okay, solenoid. Okay, for the case of solenoid, let's say you have a bar here. The coil is like this. Okay. And you put a battery like this. What is the pole generated here? This is your north or south?
North.
North. So hope everyone know this. So you have to check the battery. So current flowing here. You have to check the current flow in the coil. Current flow is downwards. So use your finger. Your finger must be acting downwards. Okay. And your thumb is pointing here. So current flowing down means your finger must be downwards. Your finger must be pointing downwards. So your thumb points your north pole. Okay. So sometimes they can put the battery like this, but the coil like this. The coil was like this. Okay, now this case on the right going to be what pole? So here current is flowing up. So use your finger, your right hand grip rule again. Now your finger should point where? Your finger, because current flowing up in front, your finger must be pointing upwards. So your thumb will be to the right, to the left. So this will be your. So remember this, solenoid. The direction, which direction is the North Pole and South Pole? Use right hand grip rule. Okay. Okay, so that's about the solenoid. Okay, next, FBIL sine theta we discussed just now. We talk about Tesla. Okay, now I want you to 2 minutes for you. These are 3 questions here. Okay. The question, the one difficult one is the second one. You can do the second one, you can do the other 2. Okay. If you check your senior videos, I've explained this, but question 2, give a try. 1 minute for you. Question 2. Get the answer in the bracket. I give you 2 minutes. Come on. Try this question. F equals to BIL sine theta. Tricky one. Okay, so managed to get the answer. 1.77 times 10^4. Wire of radius 0.1 centimeter carries a current of 1500 ampere. The density of the wire is found to be 8600. We place so that it levitates. It floats with no visible means of support. Yeah. So what do you want? What is the field to levitate it? So what is the first point you need to write? The magnetic force due to magnet must be equals to the weight of the rod, right? Weight of the rod, the wire. This is the first point. Okay, so yeah, magnetic fields what? BIL sine theta we ignore, we assume it's 90 degrees and it should be equals to mg. We want to find the B. So B is what? mg over IL. Okay, now you know the informations. Gravity, no, 9.81. Current, we know. Length, we don't know. Mass, we don't know. Okay, but density, you know. So what do you do? Anybody? The mass you change to what? Density times volume.
But we don't know the.
Yeah, we don't know the volume. But volume also we can expand, right? Volume is what?
Oh, okay.
Volume is length times the area, right? Gravity over length. So the length cancels.
Oh,
So rho A O G over I. So those who got this up to here, good. So yeah. So after this is easy. So density, you know, Area, you know, the radius is 0.1 cm and it's a circle. So we put pi r squared. So pi, pi r squared to be used. Gravity over I. Okay, then make sure all are SI unit. Then you should get this answer. 1.77 times 10 power of -4 Tesla. Okay, you try. So this is the idea. Okay, this is the idea. And the other two questions I don't want to do. You can give a try. It's easy. You don't know, you can check the senior magnetic field videos. You can, I show the working. Okay, you can check on that. Okay, so today's lesson, we discussed about what? We discussed about the most famous useful field for mankind, magnetic field. We learn about what is meant by magnetic field. Magnetic field is a region where a moving charge experiences force. Magnetic field strength defined as what? The amount of force acting experienced by a conductor per unit length, per unit current flow placed perpendicular to the field. And we found the force on a current carrying conductor, Fleming left-hand rule to be used, F equals to BIL sine theta. Okay. So next, what we're going to talk about is force on a moving charge, magnetic field due to current, and finally, we're going to talk about MRI. Okay, this is the topic about this. Okay. So I think the next tomorrow, maybe you can discuss about the third one, third and the fourth one. See how it goes. Okay. Okay, guys, I'll send you a video. There is one video in the. I send you the video. The video is about our practical. Okay, we're going to start our practical, but not tomorrow. Tomorrow, 2 hours I want to spend for theory. I'm going to spend on Friday 1 hour for practical. Okay, so before we go for practical, I want you to watch the video and do the first question. Okay, by yourself. You watch the video and do the first question, so that we can speed up, can do more. Okay, so I'll send the video. The video is on the actually on the Times. I'll label to you which video. Then you go ahead and look at it. Okay, the first question I want you to do by your own on a piece of graph paper. Do the first question. The practical book is already in the Moodle. Okay, I'll guide you tomorrow. So when you go to this, right, in your Moodle, you go to the practical session. Is it practical? This is your yes. Oh, sorry. Practical set 3 is not uploaded. Okay. I upload the practical set 3 first. Okay. So I upload first. Upload the practical. It's only set 1, set 2 is there. Set 3 is not there. Okay, set 3 I upload because you need to use the set 3. So I upload first, then I inform you tomorrow. Okay then. See you. Any questions? So no questions. Okay, see you then tomorrow.